the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through linear transformations at this point. You've already gone through the definition of a transformation, matrix transformations and linear transformations, and now we're into specialty matrix transformations. These are basically just examples of special types of transformations that are typically found in an introductory linear algebra course. They have really good applications in computer graphics, and that's why I like to use them here. All right, so let's do this. Conjecture the geometric action of the linear transformation from r squared to r squared defined by t of x is equal to ax. And if you haven't guessed it by now, that's the typical matrix transformation, just a matrix, given matrix A times a vector, where the matrix A is 1, 4, 0, 1. And we're going to do this by testing the transformation with a few vectors. And when we're done, we're going to hop over to Desmos and take a look at the visual of this. Now, this shouldn't take more than a few moments here because we get to pick our own vectors. And so I just went ahead and wrote down 3 vectors there, and we're going to do the transformation on each of those. So the transformation on 1, 1 is the matrix A times the vector 1, 1, where the matrix A is 1, 4, 0, 1. Now, just doing the dot product by rows there, we get 1 plus 4 and 0 plus 1, or in other words, 5, 1. So really hard to say what that did. It transformed 1, 1 into 5, 1. Let's see what happens with this second transformation, or the transformation on the second vector, I should say. We get 10, 3. Well, I do see a little bit of a pattern. Notice the second entry remains the same, but that first entry is kind of weird, isn't it? Well, let's try one more. And it leads us to 4, 1. Now, if you take a look again, the second entry stays the same. So that's kind of nice. Second entry stays the same, but that first entry in each of those cases changed. Maybe there's a pattern we can see to the change. Well, if in all 3 cases, if you just consider the dot product that was going on there, to build that first entry in the answer, it was the first entry of the vector times 1, and the second entry of the vector times 4. Maybe we should take a general vector to really showcase this. And you can see what happens in general. All I did was multiply or apply the transformation on the general vector AB. And in general, the second term is always the second term of the original vector, but the first term ends up being the first term of the original vector plus 4 times the second term. Visually, just to showcase what it looks like, we plugged in 1, 1, so let's take a vector that starts at the origin and goes over 1 and up 1. And after applying the transformation, which I'm going to draw in blue here, it goes over 5 and up 1. So maybe something like this. So it looks like it just gets smeared to the right by a certain number of units. In fact, in this case, 4 times 1 units, or 4b units. And you could try that on any of them. Take a look at actually the second one, which is -2, 3. Well, -2, 3, again, if that's the origin, go back 1, 2, and up 1, 2, 3. That's the original vector. After applying the transformation, we get to 10, 3. So I'll go over 10, up 3. So it looks like somebody's just smearing it to the right, and in this case, again, 4b units. Remember, b in that case is 3. 4 times 3 is 12. We started at -2. Add 12, we ended up at 10. This is called, it has a very special name, it's called a shear transformation, because you're essentially applying a shear force, or basically tilting the vector or smearing the vector in a specific direction. Let's go ahead and hop over to Desmos to see that action. So here we are in Desmos, and we'll go ahead and explore what happens with a shear transformation, specifically a shear transformation in this case. Now, you might be wondering, just looking at this, what all these dots mean. Really, they're just endpoints of vectors. For example, this dot right here is at 0.1, 0.1. And so that is the tip of the vector 0.1, 0.1. It starts at the origin and it stops, or its tip is at 0.1 and 0.1. Again, this coordinate right here, 0.5, 0.5, represents the tip of the vector 0.5, 0.5. And I can go all day long there. As you can read along the left, we will explore the matrix transformation X being transitioned over or transformed over into AX, where A is 1C, 0, 1. Now remember, ours was 1, 4, 0, 1. Well, each point in the 1 by 1 square here to the right corresponds to a vector in R squared. For example, the middle bold point is representative of the vector 0.5, 0.5. Currently in our matrix, C is set to 0. You can see it right down here. And we're going to go ahead and change the value of C to see what happens. Remember, C is in the matrix. It's 1C01. And again, our example was 1401. As I increase C, what you're seeing here are the results of the matrix vector multiplication. So our original vectors, X, are all in green, just a bunch of different vectors. Again, the vector 0.1, 0.1, or the vector 1, 1. But once you apply that matrix 1C01, maybe 1, 1, 0, 1, it shears all those vectors over to the right. It changes their X1 value. If you keep increasing that, it keeps shearing over to the right. The Y values are the X2 values here of the heights. They are not changing. It's only the X1 values. So this is a really good visual of what happens in a shear transformation. All you're doing is kind of stretching or deforming your vectors. Again, this is called a shear transformation. And there are other kinds of transformations we'll talk about, but they kind of get worked on a little bit later in this material. All right, now that we're done with that, let's go ahead and take a look at some other types of transformations that are pretty popular in the linear algebra course, at least for applications. So some examples include shear transformations, which we just had seen. We also have dilations. Dilations are when you have a mapping that stretches vectors. So it takes your original vector, you plug that into your transformation, and the result is, let's say, 10 times that original vector. So it's in the same direction, it just has 10 times the magnitude. Likewise, we have what's called a contraction. So it maps your original vector to, again, a multiple of that vector. However, that multiple is less than 1 in magnitude, so it contracts it. It basically shrinks it a little bit. And then you have rotations. And rotations take your vector and map it to a different vector where that new vector is a rotation of X through an angle. So it might take the vector like, let's say 1, 1, and it might rotate it through an angle of, doesn't really matter, let's just say 80 degrees, something like that. That's probably much less than 80 degrees. It could be 60 degrees, but it doesn't really matter. That's a rotational mapping. And there's also shifts and transformations as well. But for right now, those are the kind of the basic popular ones. Another note before we get into an example here is that all matrix transformations are linear transformations. So that is incredibly important. From this point forward, anytime that you're handed a matrix transformation, which is pretty much everything in this course, so they say, here's a transformation, it's a matrix transformation because it's a matrix times a vector, you immediately know it's a linear transformation. You may have to prove that in a homework assignment. I don't do it in a video because it's kind of a low-level proof that you could do in a homework assignment, so that's kind of nice. But there's a little bit of a wording issue with this. I dislike where I place my parentheses, so let me read it without the parentheses. All matrix transformations are linear transformations, but not the other way around. That is, if I hand you a linear transformation, it's not necessarily from a matrix transformation. Again, derivatives. Derivatives are linear transformations. They're definitely not matrix transformations. So just because I hand you a linear transformation doesn't mean it's a matrix transformation. that's just a little aside. It is a theorem, but it's such a lightweight theorem that it's nice to prove it in a homework or a quiz or an exam or something like that. Finally, in this video, let's go ahead and create a brand new matrix transformation. We get to do this. So nobody's handing us the machine that transforms our vector. We have to create the machine from scratch. We're like mechanical engineers. We have a job to get done and we're the ones that can create the machine. The machine's going to take a vector, 1, 2, 3, and it's going to do the following. And we're going to do this step by step. So I'm not going to go through all of them or say all of them out loud. You can read them if you want to. But the first thing we're going to allow our matrix transformation to do is it's going to turn off the x sub 3 value. That is, it's going to take this 3 and just turn it off. A way you can think about that, which is not actually true, but it's a way some people think about it, is projecting a shadow onto the x1, x2 plane. It's not really true because if you're doing an actual projection, the length of the vector will shrink, but let's just say we want to turn off the x3 value. So how do you even begin to build a matrix transformation like this? It comes from the fact that we know about something called the identity matrix. Recall, the identity matrix is a square matrix. In this case, I'm pretending as though it's an n by n square matrix that has zeros everywhere except for along the main diagonal. That's what this is called. And along that main diagonal is only ones. Now, we wrote this down as a theorem before, but just as a reminder, as long as the dimensions match, the identity matrix times a vector, it always returns the original vector. It's like multiplying by 1. You can see this with a very, very simple example off to the side here. You say I have an identity matrix, just a 2 by 2, and I'll multiply it by, let's say, 1, 2. Well, if you do that multiplication, you get, and this will be 1, 2, which is the original vector. So that's not a proof, that's just a justification as to why the identity matrix times a vector just returns the original vector. So let's go back and see why I mentioned that. We're going to create a transformation. And so the basis for, or the beginning matrix for our transformation, I'm going to call A sub 1 for now. And that's the identity matrix. Actually, it would technically be called I sub 3, but I'm just calling it A sub 1 because I'm saying this is our very first try at creating the transformation matrix. Now what we want to do is we want to multiply that by the vector 1, 2, 3, and then see how we turn off that element 3. Now again, I'm just showcasing the mindset. How do we create the result? Well, if you think about it, creating the result, again, I'm going to visualize this as laying this column vector on its side and doing multiplications, right? So 1 times 1 plus 2 times 0 plus 3 times 0. And then 1 times 0 plus 2 times 1 plus 3 times 0. And finally, 1 times 0 plus 2 times 0 plus 3 times 1. Now remember, we want that to be 0 in the end. But right now, it is 0 plus 0 plus 3. And we don't want that to be a 3. So how do I turn that 3 off? Well, I want to change this element to a 0. So my first try at the building of the transformation matrix, I can see that's incorrect, but that's okay because I'm adjusting it. Our second try now is like this. You can double check that will destroy the third entry in 1, 2, 3 by multiplication. And you see it does work out. So this is definitely a matrix transformation that we're looking for, at least for that first rule. We wanted to turn off the third entry and we were successful. Now we want our transformation to do more. We want to contract that shadow onto the XY plane. Right now we've turned off the third dimension, so we have essentially muted that dimension. Now what we want to do is we want to, with the remaining entries, contract the shadow by a factor of 2. That means basically divide each entry by 2. Well, think about how we were building this. If I want the end result to be half of what the value is there and half of what the value is here, then somehow I have to change my transformation matrix so that it takes half of these numbers? Well, you could probably guess just by looking at it that the transformation matrix will then change to the following. Notice that I kept in there the 0 in this position because I still want to keep that third entry muted or off. But now I'm taking 1/2 of the other entries, and that's because I want them to be contracted by a factor of 2. You could double check the work and notice after all the mathematics are done that we get 1/2 1 0, which is again a contraction of those two remaining entries by a factor of 2. So far, we're building our transformation matrix appropriately. It's done the first two actions requested. The first one was to turn off the x sub 3 value. The second one was to contract that shadow by a factor of 2. Something you should also note in the identity matrix, to turn off the x sub 3 value, we basically just turned off the third entry in the third column. After doing that, to contract the first and second terms by a factor of 2, we multiplied the first entry of the first column by 1/2 and the second entry of the second column by 1/2. Finally, and probably the most challenging one of the group, is we want to reflect this shadow across the x sub 1 axis. Now this is going to take a little bit of a thought process here. So our current vector gets the third entry removed, and then those two remaining entries, they get halved. And so you end up with something in the x1, x2 plane that goes over 1/2 and up 1. We'll just pretend as though that's 1/2 and this is up 1. So you have something like this. Now, don't get me wrong, there is an x3 plane here as well. It's just coming out of the board and I don't need it because the reality is we're allowing that x sub 3 plane to be 0 for this vector when we're done with it. But how do I reflect this about the x1 axis? Well, if this point is 1/2, comma 1, then the reflection should be 1/2, comma -1. Or in other words, we'll take that second entry of the vector and multiply it by a negative. That will reflect it about the x sub 1 axis. So I just want to take the negative of the second entry. So let's go ahead and go back to this and think about that. Well, everything here affects the first entry, here affects the second entry, there affects the third entry. Well, I want to affect the second entry. So to do that, I'm going to multiply that entry 1/2 by a -1. So I think the transformation matrix that we're interested in, which I will call A, is 1/2, 0, 0, 0, -1/2, 0, and then a bunch of zeros in the third row. And you can test that by looking at the transformation of that vector 1, 2, 3, which is our newly built transformation matrix. And let's see how this works. Now notice the resultant vector here. The third entry has been muted. That is x sub 3 is now 0. We only are looking at the x1, x2 plane. The scale of the entries for x1 and x2 are half of what they used to be, which is what we wanted. We wanted to scale them down by a factor of 2. And finally, that second entry is a negative. It's been flipped, which goes along with our picture up here. To flip about the x1 axis, we need to negate the x sub 2 term. Not erase it, but actually apply a negative to it. And that's a decent example of how to create a matrix transformation. Now, you don't actually have to do that often, but it's kind of a nice process to go through to kind of figure it out. It's a little game in a way. You start with the identity matrix. And by the way, this idea of starting with the identity matrix and building something from it will be hugely important as we move forward. So it's good to play with this when you can. It also allows you to find out on your own what the effect of changing these values will do. You should try that. Try to make this a 10 and multiply it against any vector you want and see what happens. Hint, it'll multiply a certain entry in that vector by 10. So it is a very, very good idea to practice these skills. You could just make up whatever you want. Try not to be too complex with it. I did 3 things: turning something off, scaling something by a factor, and then reflections. You will also run into problems where you have to do rotations. Those I have examples for in a different video, but I think that's enough for this video. So I hope to see you in future videos, and I hope you have a great day. Be a great human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine, just